Hello and welcome to the series called Random ML Prerequisites. A basic problem nowadays is that people tend to start using ML before understanding it completely, and that's understandable. If you are working in an industry and you really need to deploy a model and you don't have the time or the need to get into the crux of it, but suppose you want to really understand ML from the scratch, you must learn some prerequisite mathematics, or you must have some prerequisite intuition or knowledge. Even more than textbook stuff like complete derivations and everything, you need to have an intuition as to what things physically signify if you really want to understand how machine learning works. This approach that I'm going to take is largely inspired by Nando de Freitas or Nando de Freitas. I'm not sure how it's pronounced. He's a professor at Oxford University, and he has those great open source lectures online, and I think you should go and check it. What's going to happen in this series is I'm going to basically pick a topic mainly at random, as the name suggests, and I'm going to go into mathematically breaking down that topic. There are going to be some prerequisite knowledge. For example, today what I decided is that I'm going to discuss Gaussians. I'm going to discuss Gaussians, what they mean, what they signify, how important they are to ML, and learning how to model Gaussians. Basically, we'll get into that as we progress through this video. However, I'm going to require that anyone who observes this video knows what a mean is, knows what median. Sorry, I don't need median and mode in this video. You must know mean, median, and mode anyway. You should know what variance and standard deviations signify. You should know what is actually basics of linear algebra. So linear algebra basics, nothing much. You should particularly know matrix multiplication, inversion of matrices, etc., etc. The absolute basics, nothing too deep in linear algebra you'll need here. And probability. So though I would be discussing a lot of probability in this, but I need you to know absolute basic what probability means. Because when we are talking about Gaussians, we are talking about the Gaussian probability distribution function, PDF as they are called. So what is a probability distribution function? So supposing you have a random variable, this is also a statistically significant term, a random variable. Supposing you have a random variable, which is basically, as the name signifies, a variable that can take a random value. So you have a random variable that can go 1, 2, 2.5, so on, several possible values, maybe even infinitely possible values. So supposing you have this random variable, and as you can see, it can take certain discrete possible values. So this would be known as a discrete random variable. And if you have a function that can model how likely this random variable is to take any one of these particular values, then that function would be known as the probability distribution function for this random variable. This is absolute basic. I'm not going to go ahead and discuss that in detail. If you cannot understand that, then you should probably or maybe I'll make a video later. If you cannot understand that, maybe I'll make a video later explaining random variables and random processes in detail. So what I'm going to do right now is that I'm going to say, take an example of a continuous random variable. So what if this was continuous? So what a continuous random variable would be is, supposing x, it would be something that can be any value. It could have, I can't put an equal to sign over here because what I'm writing on the right side is not like the correct mathematical notation. This is just to make you understand. We will be writing mathematical notations. So continuous random variable can have any value within a range. Suppose a random variable between 4 and 5. So it can be 4.2, it can be 4.3, it can be 4.141414875, it can be anything. So what I mean to say is that it can be anything. There is not a discrete or a quantized state that it will be like, it's not quantized. So what it means is that it's not a set of discrete values that it can take. It can take any value, right? Any value. So for example, supposing if a random variable was between 2 and 6, then that random variable could even have pi as a value, even though that's irrational, but that can be a value. If you don't put a constraint on it, it can be a value. So what I'm going to do right now is I'm going to go ahead and look at probability distribution functions, and we come to Gaussian probability distribution functions, and we'll get into one concept after the other. I think this is going to be fun if you are mathematically triggered per se. So what I'm going to do is, first of all, let us see what a probability distribution function looks like. So let's start with Gaussians itself. So Gaussian, or people also call it the bell curve. How they look like? They look like something similar. So, God, I'm terrible at drawing. I'm terrible, absolutely terrible. Alright, I'm going to accept that. I'm going to accept that state as a state. So let's go ahead and plot Gaussian. So this is how they look like. The height or the amplitude signifies how likely, or let's say px and x. So as you can see, this is a continuous random probability distribution function, because it's defined for all values of x, right? Not at discrete values of x. So for example, if I'm to take this value of x, any value, and say x1, and I look at the height, so that is how likely x1 is to occur. However, clearly x2 is more likely to occur. x3 is much less likely to occur. And something like far into infinite, so at minus infinity, maybe this line is so close to this line that the probability is 0 at that point. So that would be an asymptotic relationship, so it would fade into 0 amplitude, suppose, at infinity, if you can reach infinity. Get that? Anyway, so what I'm going to do is I'm going to mathematically model this probability distribution. So every probability distribution, along with a graphical modeling, should always be, if it's a mathematical function, then it has a mathematical formula. So how this can be defined is, alright, so that is one scary looking formula for me, at least if I'm a beginner. So let's break it down, let's understand it. So x is obviously the value I'm considering, like the value for which I want to consider the probability. If I'm plotting this function, then obviously I'm getting a locus, so x would vary from minus infinite to infinite. X would vary from minus infinite to infinite. What is mu and what is this sigma? So let's go over this. Mu is this point. So mu is known as, the mean of the mean of the probability distribution. We would what mean is, what I expect from the prerequisite knowledge of mean is only that you understand mean means the average. So if you have 5 numbers, then the mean of those 5 numbers is a summation of those 5 numbers divided by 5. So that much. We'll get into the physical interpretations of these. And sigma square sigma is the standard deviation. So sigma square is the variance. Alright, we have the tedious bookish definition out of our way, and now let's we need some more tedious bookish knowledge after this. So this is obviously a known fact that if you sum all the possible probabilities for an event, then it's going to sum to 1. So for example, since x varies from minus infinite to infinite, if you were to integrate px dx from minus infinite to infinite, you would get 1. Or graphically speaking, the area under the bell curve is 1, right? Because integration means area. Okay, so now let's look at this formula once again. We need to understand things from this formula. So x is obviously the input to the function. Now other than x, which are the two variables in the function? Pi is a constant, 2 is a constant, half is a constant, e has a fixed value. So I mean, this e to the power x is a fixed function. This is not e 2.7, not that e, this is a function. So what are the two variables in the function, right? So mu and sigma, these are the two variables, or rather mu and sigma square, because I only see sigma squares. So I can just take sigma square and mu, and these two variables would define the nature or the shape of the Gaussian. So these, for example, if I say this point is mu, that is the highest peak, I mean the peak of the bell curve corresponds to mu in the x-axis. So suppose that is the case. So if mu were 0, if mu was to be 0, then obviously this would be my bell curve. However, if I shift mu to be 0.25, that would be my bell curve. Now for example, standard deviation. Now what would standard deviation signify? It signifies how quickly this Gaussian fades out. So standard deviation, if you know the physical significance of standard deviation, so it is how much does my data distribution vary from the mean. So if I have the mean at the center, so it would mean that how much more probable are the data points further away from the center. So if you have a high variance, that would mean that you are very slowly decaying. So for example, if variance were very high, then maybe this could be the bell curve. For the same case, however, for the same mean, if the variance is low, then maybe you have a sharp bell curve like that. So those are the nature. So basically mu and sigma square defines the nature of the Gaussian for any given input x. These two are known as sufficient statistics, because the knowledge of these two parameters, or these are also known as the parameters or sufficient statistics. So the knowledge of the two sufficient parameters would help you to model the entire function. So that's the reason behind that fancy name. And n mu sigma square, n stands for this is the mathematical notation of any Gaussian with mean mu and variance sigma square. That is the crust of that formula. Now what we would want to do is, now if you look at the formula right now, then what has happened is that we have taken a value x, right? So you have taken a input value x and you have modeled the Gaussian from that. So how do you do the reverse of it, right? How do you come back? Like, how do you take a value out of a given Gaussian? So we need to go ahead and look at this interesting process. Suppose if you find this interesting, even if you don't find it interesting, go out and play table tennis or badminton or cricket, something like that. So this process is known as simulation. So what simulation is or hallucination? So what simulation and hallucination is that you want to find a value x which is sampled. So that's the notation. This is sampled or hallucinated or simulated from a given Gaussian. Now what I would typically means what typically systems do. I'm just going to go ahead and show that. So suppose I have the coordinate axis like this, and I have a Gaussian like that. Now this is the probability distribution function PDF. Now let us look at the cumulative distribution function CDF. So what CDF is, at any point it is the area from minus infinity up to that point, or the summation of all the probabilities up to that point. So if I were to write the CDF as some fx, it would be minus infinite to x, summation of everything up to this point, px dx. Alright, so I know that the entire area sums to 1, right? So when you have summed all the probabilities, you should reach the value 1. Correct. And how this would basically look is, so this is clearly mu. Let me just get that point down here. Now, if you would have a look at this bell curve, then all the this is bell curve is symmetric about mu, right? So whatever is on the left side, area left of mu, that area is the same as the one right of mu. So you will have the value half at mu if the total area were 1. So you would get a curve that is sort of like this. Pardon my drawing skills, but that's the best you have today. So that's the curve that you would be sort of getting. So if you have a coordinate axis, suppose like this, between 0 and 1. So if you can get a random value between 0 and 1, you can get a random value between any range, right? So if you have a random value between 0 and 1, then multiply it by some magnitude m, and then you would have a random value between 0 and that number. So you can easily do it, and then maybe some addition subtraction to shift the range left and right. So any random number can be generated if you can generate a random number between 0 and 1. So what if I were to have this behavior? I mean this probably what I mean by behavior is the randomness of this probability distribution function simulated by this Gaussian, and I want to get a point out of it, right? I really want to get a point out of it. So what I would do is I would take a point over here, right, over this cumulative distribution function. So once I have done that, I would go ahead up to this height. So this is not drawn to scale, and I will not be able to show this if that is not drawn to scale. So let me go ahead and erase that. Should I hide my mistakes when I edit the video? Maybe not. Maybe I'll leave it like this. So I am going to just take this scale itself. So this is 1. Zero. and this is 1. So basically even the area of this is 1, right? This area also corresponds to 1. If you take this area, the summation is going to be 1. So what I'm going to do is, once this is done, once you have a point over here, you look up the corresponding height amplitude over here and go ahead and project that, and this value, say x, is your simulation or is your sampled value from the distribution. So this is one way out of several ways that sampling could be done from a probability distribution. You have to go through the cumulative distribution function. But we have been talking about Gaussians and all this theory for so long. But why should you continue watching this video? I mean, why should you learn Gaussians? So what happens is Gaussian is the most natural random function out there. So if you were to take a naturally occurring event, say the tests of students in class. So supposing I were to go ahead and record the marks of all the students here taking tests in a class, and if that was I have a significantly workable number of students. So supposingly I have a test of 100 students, then I would see the probability distribution approach a Gaussian. Like, suppose these are the students who have got between 40 to 60 marks. This is below 40 marks, and this is above 60 marks, and these are the select few who have scored above 90 marks. That is how real life stuff happens in general. So most of the times you will be working with data that is distributed as a Gaussian if you are working with such real-time data. The other thing that is of interest is that in various ML techniques, you would be, or especially adversarial learning, or even maybe if you are dealing with noises in machine learning, so, or deep learning. So what would happen is that you would be using Gaussians. Reason? So there's a very interesting analogy that you could come up with if you have studied communication engineering. There is this concept in communication engineering which is known as the central limit theorem. Central limit theorem. So what it says is that supposing I have a random variable x1, I have another random variable x2, I have another random variable x3, I have another random variable x4, and I take the summation of all these random variables, right? I add them up up to, say, xn. I add all these up to xn and I put it in a random variable x. So according to central limit theorem, when n tends to infinite, that is for infinitely many random variables, if you had to sum infinitely many random variables together, you would approach a Gaussian. So in a way you are modeling a lot of randomness if you are using a Gaussian. So if you are using a Gaussian to insert noise into your model, you might not be theoretically inserting any sort of bias. You might not be inserting any sort of bias into the model due to the noise. So that's a really interesting property that you might get from a Gaussian. Correct me if I'm wrong about that. This is something that has come up to me as an analogy from communication engineering. So I think that's really cool. So what I am going to do right now is that I'm going to go ahead and take this concept further and discuss what is the significance of the mean in a probability distribution function. So I'll have to draw a proper Gaussian for that. So with everything, right? So let me take a Gaussian. Done. Now, according to what I have discussed so far, that's the mean. That's mu, right? So In general, there's this notation in probability distribution functions which is known as the estimation of the distribution function. So estimation usually means not usually is the mean. So what is the physical significance behind calling this the estimation is, supposing I were to remove this Gaussian completely out, like I would just take off this Gaussian and I would just replace it by a single scalar value. So which scalar value would appropriately, like no scalar value can perfectly like define a random distribution, right? So however, if I were to replace it by a scalar value, then what would be the scalar value I would be using? It's funny, right? So that is the significance of estimation, and clearly in this Gaussian, the most probable value to occur is the mean. The further away you go from the mean, the less likely are those values to occur. And so if I were to replace this entire distribution by any particular value, I would replace it by the mean. So the mathematical definition of estimation would be, when I'm writing an integration out of the blue, please assume it's from minus infinite to infinite. So x px dx, and this is mu. This is also 1 by n into summation I is equal to 1 to n xi for discrete observations. So even so such integrations converging to such sums, this estimate is known as the Monte Carlo estimate. And such estimations are valid for large values of n. So obviously, if infinitely many discrete values were there, when you look at it as a whole, you might be just observing a continuous value. That could be the physically means that could be your physical takeaway from such a statement, like this is valid, such an equality is valid for large values of n. So I think that we have come to a point where we sort of understand that why I am learning about the Gaussian, and maybe even some things about the Gaussian itself. We have got some things about the Gaussian itself. So we need to understand, before I go further, to discuss what two variables Gaussians looks like or multivariable Gaussians looks like. So we need to understand what covariance is. So covariance denoted by say, like we could write it as COV x comma y. So what covariance is basically, it defines how related two values are with respect to each other. So covariance x comma y, where x comma y are in statistics known as assets. So how related are these assets with respect to each other? If the covariance is 0, we could say they are completely independent of each other, they have no relation. If it is positive, we say that they positively covary with respect to each other, meaning that if y increases, x increases, right? And if it is negative, then we could say they negatively covary or inversely vary with each other. So if x increases, y suppose decreases. So that is the physical significance of covariance. There is a very tedious formal definition. So covariance of two variables would be the estimation of this distribution. Right. So this converges to minus estimation of x, estimation of y. Let us now, for example, look at some value, say suppose x and y. Suppose we have some data points like this. Even though I plotted these at random, what you would observe is that in general, a greater value of x has a greater value of y. So I would expect positive covariance over here. Then again, if I were to simply take something as random as this, then maybe this is zero covariance. So x and y are not at all related. You can't have a formal relation between x and y. Alright, with that said, we have used x and y as, like, we have treated x and y as a single axis thing in the previous graphs. However, in machine learning, what would happen is x is a d-dimensional vector. So x would be something like this x1, x2, x3 up to xd, right, up to xd. So what happens is you could define something called the covariance matrix. So what covariance matrix is, it sort of defines how each axis of x is related to the other, right? So how each axis of x is related to the other. Another thing you should probably know is that covariance with itself, so covariance x comma x is just the variance of x, right? So that's another thing you should know. Now let's go ahead and, it's interesting, if you would try to physically think about this physically, why this is true. So that's something that I would leave it up to you. If you can't find it, maybe put it up in the comments and I could do a video on that. That could be very interesting 5 minutes video. So let's look at a covariance matrix of x. So if x is this vector, so what it would be is that it would be this two-dimensional matrix, right? It would be this two-dimensional matrix. So firstly, on the first thing, we would have covariance of x1 comma x1. So I'm just writing that as variance of x1. The second element would be covariance of x1 comma x2, so on, covariance of x1 comma xd. So here we would have covariance of x2 comma x1, covariance of x3 comma x1, go on up till covariance of xd comma x1. Along the diagonal, we would have variance of x2, variance of x3, so on, variance of xd. So clearly this element would be covariance of, so sad I couldn't get that right, covariance of x3 comma x2, yep, x3 comma x2. So these are how the values would progress. This is obviously a huge matrix and we would never have to calculate this by hand. So let's see why I said that is important in order to understand Gaussians. So let's try to understand what a multivariate Gaussian is. Multivariate Gaussians. So the first thing that I would like to do is I would like to understand means what is this multivariate Gaussian. So let's look at the 2D reduced sample of it, which I can plot on paper, though even that would require a third axis which you would have to imagine. So let me take this x and y. Both are random variables. Note, both x and y are random variables. Suppose this is the graph of x, right? X is a Gaussian. This is a graph of y. Y is also a Gaussian. So what would be the Gaussian xy combined, right? If xy, I take it into one single graph, how would I do that? So obviously this region, right? These majority regions in the Gaussian would also come in the resultant to a multivariate Gaussian. This would also, or 2D Gaussian, this would also be the most probable region for the values to occur, right? So I'm using the concept of contour plots. So in contour plots, suppose this is a contour plot. So in the region where the lines are close to each other, values are higher, right? So in terms of probability, in the regions where the lines are closer to each other, values are more likely to occur. So here it would be very highly likely to occur. And as we move away, the lines should move further away from each other, right? So I think something like that. And further and further away, it should be less and less likely. It should be less and less likely, right? So further and further away, it should be less likely. That is, the lines should be further away from each other in the contour part. So that's not a perfect drawing. I can't draw perfect. Pretty terrible artist. So what's going to happen is that if you would look at this in this region, it is highly likely to get a value for the Gaussian. So this contour plot, this is the 2D Gaussian. That is the 2D Gaussian. So you could look up images of the 2D Gaussian. I could pull up an image over here, but you need to understand and learn to infer from the contour plots itself. Because 3D, 4D, 5D, how long I'm going to go about it? At some point or the other, you have to project planes into lower planes and understand what they mean. So I'm going to draw the line here itself, and I'm going to leave this contour plot as it is. I'm not going to pull up a 3D image from the internet and show you guys. You could look it up though if you fail to understand contour plots, but then again you should go ahead and study contour plots from vector calculus. Now what I would do is I would take 2D points, so x1, x2 as a like the random, like I had taken this d-dimensional vector, I'm taking x1, x2 a 2-dimensional vector, and both x1 and x2 are suppose random, and x is a random variable which axis x1 and x2, and I am going to sort of try to find the expression of the a Gaussian like this, an expression of a Gaussian like this which models x, right? So x1 could be this x, x2 could be this y, suppose, and let's say the Gaussian distribution of x is this distribution, and I want to find the equation for this distribution. I want to understand that distribution. I want to see why covariance is important. Learning covariance is important. So let's go ahead and do that. What I'm going to say is x1 is a Gaussian, right? So just like I drew it over here, x1 is a Gaussian. So I'm going to use this mu1 sigma square. I'm going to take the same variance for both of them. So they decay the same, just to prevent the complications of calculation. Mu2 sigma square. I've taken different means. So there's this concept of the joint probability distribution. So the probability distribution taken when x1 and x2 are combined together, right? So x1 comma x2, it's written p x1 comma x2, and How this would work is you take the probability distribution of x2 given that x1 has already occurred, and take the corresponding probability distribution of x1. Now what we would do is, if x1 and x2, supposing x1 and x2 are independent, then you could write it as px2 into px1. If provided that x1 and x2 are independent, we are going to make this assumption. So as of now, what is my random variable? It's x with x1 and x2, given that both x1 and x2 are independent of each other. These are independent of each other. Like the way I'm progressing with my derivation, that is definitely the case. Now let me get a new page. What I would do now is that I need to mathematically find some relationship between them. So let's take the covariance of x first. So what I have is variance x1, covariance x1 comma x2. So I'm denoting this covariance matrix by capital sigma. So variance x1, covariance x1 comma x2. Then I have covariance x2 comma x1 and variance x2. Now since I have assumed that x1 and x2 are independent of each other, and I know that the variance of x1 is sigma square and the variance of x2 is also sigma square from these two lines. So here they are. These are the variances. So I'm plugging in those values, and what I have right now at hand is sigma square 0, 0, sigma square. Now we have come to the part where we need to do some tedious calculation. So this series is definitely going to be mathematically intense, but then again, that's what this is about. Otherwise you could just go ahead and learn sklearn. What I am going to do right now is I should derive the 2D Gaussian distribution expression. So let's go ahead and do that. So I have come to this formula so far. Like my derivation so far is px1 comma x2 is px1 into px2. Since they are independent of each other, I had come to this already. Now I am going to replace these two by their formula, like what I have already learned. So 1 by root over 2 pi sigma square e to the power minus 1 by 2 sigma square x1 minus mu1 whole square. That's px1. Then I have 1 by root over 2 pi sigma square e to the power minus 1 by 2 sigma square x2 minus mu2 whole square. Alright, now what do we do? So what I see is that I have got this 1 by 2 pi sigma square thing, absolutely the same. So I'm going to take that in. So it's going to be 1 by 2 pi then sigma square. Now what I have to do is I have to look at this exponential part. So e to the power, what I have is minus half x1 minus mu1 x2 minus mu2. Like I have x1 minus mu1 whole square into x2 minus mu2 whole square, but what I'm going to do is I'm going to use this sigma square thing over here, right? So I am going for a matrix notation, like I am going to put this sigma square over here. So I am going to do x1 minus mu1, x2 minus mu2, and I am going to put in that sigma square value over here. So that's sigma square. I'm multiplying each of these elements by sigma square. So sigma square 0 0, and obviously it was in the denominator, so I'm going to go ahead and put a minus 1 over here. Alright, pretty intense, pretty intense. Let me look at what the determinant of that covariance matrix should have been. So that should have been sigma square 0 0 sigma square, this determinant, which is nothing but sigma to the power 4. So what we have here is nothing but 1 by 2 pi sigma half, yeah, e to the power minus half. So let's shift the entire thing to matrix form. So what I have is this basically. So x should be x1, x2. Mu matrix is mu1, mu2. So let's go ahead and do that. So this would be x minus mu. This is sigma inverse and x minus mu. So x minus mu, this notation as a column vector, so that would be the normal thing, and the row vector thing would transform to a transpose. That is the expression for a multivariate Gaussian. This thing is a multivariate Gaussian. So I think we have covered a significant bit today. Let us quickly have a look at it. So we have covered a Gaussian, we have covered multivariate Gaussians, like two variable Gaussians, and we that this final expression for a Gaussian, if you would observe that since these are matrices, right, these are matrices, so this value extends to any number of dimensions. So even for say a d-dimensional thing, this would be valid. I can't draw that on paper, but this would be valid. It has come up here. That's because there were two values and the root got cancelled, because root 2 pi into root 2 pi is that. So however, in general, for d dimensions, your solution would converge to something like this. So 1 by this 2 pi, you would have d such root 2 pi's, so they would converge to 2 pi to the power d by 2. You have this mod sigma to the, everything else remains the same actually, because we have shifted to the matrix notation for everything else, so those remain the same. I'm going to write capital X for matrices, so I'm going to use capital X for matrices. So xx, so mu transpose sigma inverse x minus mu. So there you go, valid. I can't draw that on paper, but this would be valid. So this entire thing is valid for any number of dimensions. We learned what covariance is, we learned what they signify, we have seen what uh, they look like when what zero covariance means. I mean, we have seen that independent variables do not have any particular covariance. It means they have, I mean, they have zero covariance. We have learned the Monte Carlo estimate that converges certain integrals to certain sums for large values of n. We have sort of had an analogy between the central limit theorem and Gaussians. We have seen why Gaussians are important in machine learning, and in general we have learned simulation and hallucination from probability distributions and the Gaussian and bell curve yada yada theory. So I think that is it for today, and maybe we'll come back later. I mean, I do want to come back. I will come back later. Yes, I will come back later with more. Maybe next time we will come learn something like the principal component analysis PCA. Suppose that's fun. Maybe we will. I mean, I am also going to do a series on machine learning topics like linear regression, the math entire part of it, logistic regression, the math entire part of it. Maybe we will look at things in a different way in this series also. Like linear regression, we would solve it using least squares in that series, and maybe come back here and solve that using maximum likelihood estimation probabilities, because what's stopping us. And this would be really fun if we go on with this. So thank you for watching the video. If you like what you see, then go ahead and hit the like and subscribe button. See you.